And look at that. Look at what I've got. In this particular resonance form, I see that I really have a protonated amide. All I have to do is come and use one more equivalent of water to pick up that acidic proton. And lo and behold, as part of this hydrolysis, I've made this molecule. Look carefully at that molecule. If I just allow that carbon-carbon bond to spin, I think it's going to look somewhat more familiar. It's just an amide. So I started with a nitrile, and what I found is that by subjecting it to H3O plus H2O conditions, I produce an amide. Under these conditions, however, the amide itself is not stable. The amide will continue to hydrolyze all the way to the carboxylic acid. That would be a good exercise for you to see if you can continue the reaction all the way to the carboxylic acid. I will tell you that since you've got an amide with a carbonyl oxygen and you're under these acidic conditions, for sure the first thing you want to do is protonate that carbonyl oxygen. That produces a super electrophilic carbon, which can add water, and you're on your way to a carboxylic acid. Bottom line, though, is that the nitrile can be hydrolyzed under these acidic conditions to a carboxylic acid. That's a very interesting reaction from a synthetic perspective. Because what I want you to recognize is that a moment ago we talked about how to make nitriles by bringing in a cyanide anion nucleophile and conducting an SN2 reaction. That allows us now to think about synthesis problems like this, where I start with a 4-carbon substrate in which I have a leaving group at a position suitable for an SN2 reaction, and this happens to be on a primary carbon, so that's good. And what if I want to convert that into a 5-carbon carboxylic acid? Well, this would have been a pretty challenging problem for us just a few minutes ago, but now we have a way to do it, and to do it quite efficiently. We can, in the first step, treat this with cyanide anion. That adds our 5th carbon right there. That's an SN2 reaction and a beauty. And it allows us to stretch, if you will, our 4-carbon substrate into a 5-carbon substrate. And now I know that nitriles can be hydrolyzed under these acidic aqueous conditions to the corresponding carboxylic acid. Organic chemistry is all about building larger and larger and hopefully more useful organic compounds from smaller ones. What's nice about this reaction sequence is it allows us to increase our carbon count. We go from 4 carbons to 5 carbons, and that's usually the sort of thing that is quite useful. All right, so nitriles. We've looked at 2 reactions so far. We've looked at hydrogenation and we've looked at hydrolysis. We've got 1 reaction left, and it's a beauty. One of my favorite reactions. You might remember from class recently that if you took a carboxylic acid, so I want you to recall that if you took a carboxylic acid, let's say we start with benzoic acid, and you reacted it with 2 equivalents of an organolithium. So let's say 2 equivalents of a methyl lithium in the first step, and then in the second step you add H2O, H3O plus. This was that fascinating reaction which actually produces a dianion which is stuck. It can't go anywhere until you quench it. You quench it and you produce a geminal diol, which just immediately re-equilibrates to the corresponding ketone. So this was a really clever way to convert a carboxylic acid into a ketone using an organolithium. So we covered that in the carboxylic acid chapter. Now, what we're going to do right now is to look at a very similar reaction, except instead of working with a carboxylic acid, we're going to use the nitrile. And here we go. I'm going to go ahead and I'm going to add the same organolithium species, which in this case is methyl lithium, and look what happens. Not surprisingly, addition takes place at the carbon which mimics a carbonyl carbon. That's the electrophilic carbon that's attached to the nitrogen. And just as in a nucleophilic addition to a carbonyl carbon, I've got to break one of those pi bonds, kick the electrons onto the heteroatom, which in this case is nitrogen. So what I've got here is my methyl from my methyl lithium has added to my nitrile to produce this imine-looking structure, which is actually an anion. Now, if this were a ketone, it looks a lot like a ketone, doesn't it? If this were a ketone, a second equivalent of this organometallic could come in and add. In fact, that's what we see with acid chlorides and esters. We've already been through all that chemistry. You can't stop the reaction after one equivalent has added. You've got to bring in a second equivalent, so you just go ahead and work with an excess, recognizing that it's a losing battle, you may as well use an excess. But in this particular case, it doesn't matter if you've got an excess or not. This reaction has to stop here. Think about what would happen if a second equivalent of methyl lithium tried to add. The nitrogen's already got a negative charge. What would it do? Produce a 2 minus nitrogen? Not going to happen. Nitrogen cannot accommodate a negative 2 charge. So it's got to stop right there. It's just stuck. Can't go anywhere else. What you do in a separate second step is add H2O, H3O+, just like we did up there. And when you do that, you form the imine. This is an imine. But what's so fascinating about it is that this imine is formed under these conditions, H2O, H3O+. These are hydrolysis conditions. If you think about imine formation, we would have taken a ketone. This is how we made imines a couple weeks ago, or really just a couple days ago in this summer course. We would take a ketone and we would react it with an amine, a primary amine, in the presence of a little acid catalyst. It would produce the imine plus water. In order that the reaction didn't re-equilibrate and favor the starting materials, the ketone, we had to get rid of the water. But if you take an imine, or an enamine for that matter, or an acetal for that matter, and you treat it with H2O, H3O+, you will, by Le Chatelier's principle, drive the equilibrium back to the ketone. That's exactly what's going to happen here. We didn't start with a ketone, we actually started with a nitrile. But this imine doesn't know that. And if we're working under these conditions, H2O, H3O+, we will just immediately and uncontrollably drive the equilibrium back to the corresponding ketone. We make the same exact ketone we made with the carboxylic acid up here, where we required 2 equivalents of phenyllithium. The reaction of phenyllithium with a nitrile only requires 1 equivalent, but in that quench step, you make exactly the same material. That's fascinating. I'm going to go ahead and erase this and just summarize what we just did without the mechanistic detail there. So I've still got up above this reaction of a carboxylic acid and 2 equivalents of a methyl lithium in order to produce the corresponding ketone, a methyl ketone, since I started with a methyl lithium. It turns out I can get there from a nitrile as well using 1 equivalent of methyl lithium. You can use an excess if you like, it wouldn't matter, but you only need 1 equivalent. And then in the second step, H2O, H3O+. Almost identical reaction conditions, taking the nitrile to the same methyl ketone. So you can see why it is, in these last 10 minutes we've been discussing various chemistries of nitriles. You can see why it is that we treat the nitriles with the carboxylic acid derivatives. They are so similar in terms of their chemistries. Well, with that, I think I have finished all of the reactions I wanted to show you. This is a chapter on carboxylic acid derivatives. And the bulk of the chapter dealt with nucleophilic addition-elimination reactions. What you should definitely know about those reactions is that the acid chlorides are the most reactive of the carboxylic acid derivatives, and they do all of the nucleophilic addition-elimination reactions with ease. As you move down to anhydrides, they're still pretty reactive. You get down to esters, less so, and certainly by the time you get to amides, they're not very reactive at all. Now, having said that, there are some other reactions which are important. We showed, for example, the addition of organometallics to acid chlorides and to esters in order to form tertiary alcohols. We showed the addition of metal hydrides like lithium aluminum hydride to both acid chlorides and esters in order to make primary alcohols. And we showed in both cases ways in which we could stop the reduction at the aldehyde stage. Different sets of reagents to do it, whether we started with an acid chloride or an ester. Finally, we showed that the nitriles themselves have a very interesting chemistry. They can be produced in an SN2 reaction. They can be hydrogenated to make primary amines. They can be hydrolyzed to make carboxylic acids. And they can even be converted into ketones using a very similar sequence that we had up here for carboxylic acids. That concludes chapter 19, is it? I don't even remember. Chapter 18, derivatives of carboxylic acids. So we're all done, and I hope you work on the homework problems religiously. When you come back on Monday, or I should say when I come back and meet you again in class on Monday, I think I'm going to spend the bulk of that class period going over homework problems with you. Homework problems in the back of chapter 17 and also in the back of chapter 18, preparing you for the exam. So I'll see you then.